So using this question that we are given, I'm going to explain the concept that you have when you are given a coil and a capacitor in parallel. Considering that the current of the resistor, that is the current flowing across the resistor and current across the inductor, it's a combined part that you are given. It becomes this part here, this resistor and this inductor is considered to be taken as a coil. That's our coil. So we are given in this case, calculate the following using the information from the circuit. This is what you're given, and this and that, the phase angle of the inductive circuit, this and that. Okay. So remember, the same circuit, they can refer to a condition when this circuit is at resonance. It's another part which is totally different. There you are taking this as a normal circuit that you are used to. So we are given the resistance of 75 ohms and the inductance, which is 200 millihenries. And we are given the capacitance of this capacitor as 150 microfarad with a voltage of 180 at 50 hertz. And this is the total current that we are given, the current flowing across the capacitor. And this is the current that is flowing across the coil, that is RL, where the resistor and the inductor are combined together. These two, they are being combined together. That is to give us the impedance of the coil, which is at RL. So the question is, in this case, calculate. So I'm going to talk about this as I'm referring to this question. You can also refer to any question that you answer of this nature. All right, 2.1. The phase angle of the inductive branch, 6 marks. You wanted to say 6 marks. How is that so? Okay. It is because across the inductive branch here, if we are to consider properly across the inductive, where we are given the inductor here, across this branch here, across this branch, there is a resistor. There is a resistor. So you must work with what is affecting the resistor and the inductor, which is the ZRL, the impedance of the coil. All right, so these calculations, I'm going to explain one or two from this part. I explained about the parallel circuit so that you can understand me on the other part. So on the parallel circuit, these are parallel circuits, all right? But when you are working with this condition of a coil and a capacitor, you are going to work with these formulas. I'm going to explain these formulas of the components, all right? These formulas affecting the components, all right? What else? What else? Yeah, so this is what you're going to have. So in actual sense, this is what you're going to have. So the part, it's not like everything. You're just talking about three formulas so far that we are seeing here. So the rest, you have to understand. So this is what I'm going to explain from this part. Let me check here another part. I want to just be sure before we move on. Because you're right. So this other part, remember, it's for a series. I wanted to see if we can have another formula. So there we do not have any formula that we are going to relate back there. Okay, so this is it, no problem. So these are the three formulas that you are going to put into consideration with other formulas that I'm going to explain here. It follows that, remember, this here is a series. This one, the resistor and the inductor, they are in series. The resistor and the inductor, they are in series. I want you to get back to a normal RL circuit. Let's go back to an RL circuit in series. What are the properties of an RL circuit in series? Okay, because there's a resistor there and an inductor. They are in series. What are the properties? If you understand these properties, guys, you are done. I want you to see something. Okay. This is how you're calculating. You're having your resistor, your inductor, the voltage, which is total voltage, the total current. Okay. With this, you were calculating the total impedance as Z. You're just calculating Z as usual. The total impedance Z is equal to using the phasor sum, which is R squared plus XL squared. This is how you're calculating. Guys, the same manner that you're calculating this, but now you're considering to say is ZRL, to say is a single part is taken as a coil. But it's the same. It's a series that this is in series. The resistor and the inductor are in series. So therefore, it follows that this impedance, which is our ZRL, is still the same formula that we are used to on an RL. Go back to the RL circuit. The properties of an RL circuit, what do they say about an RL circuit? But just that you're considering as ZRL, to say we're combining the resistor and the capacitor and the inductor. But it's the same thing. Okay, I do not want to refer to this part much. I want us to consider the question, because the question is on the phase angle. So this is the reason why I'm talking about the impedance. Remember, when you are dealing with a normal RL circuit like this one, a normal RL circuit that we are used to, this is how you're going to present the phasor diagram, talking of the impedances, all right? This is your Z, okay? That is your Z. This is the resistance, and this is your XL. Remember, your XL, according to this part, you're going to have L on top. In a normal, considering a normal RL circuit, we know that VL leads the current, that is the current legs, meaning to say we are going to obtain XL, everything about the inductor will be on top. So that is the idea there. Where this is the theta, which is the angle that we are obtaining. This is guys, I'm explaining on your normal RL circuit. On your normal RL circuit, how were you calculating? And I said on a normal RL circuit, as long it's a series circuit that you're considering, as long you're considering a series, we are back to the series circuit. How do you calculate the phase angle theta? Arc cos of R over Z. It's arc cos of the resistance over the impedance. So in this case, it's the thing that you are using here, arc cos the resistance over the impedance. But now we are considering this angle, because this is no longer the Z, like this is, it is the same Z, but we're just considering as Z RL, like the coil, considering the resistor and what? The inductor. This theta is the current, is the phase they're talking about between, which is taken in the inductive branch. So it's called theta L. So instead you can call this theta L, which is given as arc cos the resistance over Z, which is the Z RL that we are given, just like that. So it is the same. So you root out this, take it out, and consider it separately the way that you are used. We are used to this. We are used to this. We take it out of the circuit. It's a series circuit that we are used. This is a series circuit that you are used to. So that's how you can answer this question. So as you can see, we can calculate the phase angle from this formula. So that means, guys, we are going to need, according to that formula, we are going to need this impedance, which is XL. We do not have again, so you're going to calculate XL. We have got the inductance there. So remember that XL is taken from 2 pi FL. That is, XL is 2 pi times the frequency, which is 50. That is, the frequency is 50. The inductance, remember, is 200 millihenries. That is 200 times 10 to the exponent of -3. So this was going to give us XL, which is 62,832 ohms. All right. So with our XL, we can calculate our Z, which is equal to the square root of R squared. Remember the resistance, that's 75 squared, plus our XL, which we calculated, which is 62,832 squared. So this is what you're going to have. So we've got the impedance that is affecting the part of the inductor, the coil. So this is going to give us this impedance of 72,841 ohms. So the reason of calculating this impedance is because we saw this part here. We saw it from our formula. The theta, which is the phase angle that we are going to need, is arc cos of this from our normal RL circuit. That is why I had to explain this so that at least you can get the sense where it is actually taken from. So you can calculate theta there. So that is theta, which is the phase angle taken across in this inductive circuit, is equal to arc cos of R over ZRL. So that is, in this case, is just a matter of substituting the resistance. We are given 75, then the impedance that we calculated, that's 97,841. So that was going to give us 39,955 degrees. So that is the theta, the phase angle of the inductive branch that we are given. All right, so that was with the 6 marks, and we talk of the current. That is the current IRL, the current across this coil. That is this current across the coil. Remember, you are working, or you are given a condition where this is in parallel. And we know that the voltage is the same in a parallel circuit. And you calculated the impedance of the coil. This is the impedance of the coil. So we can calculate the current that is flowing across. All right, so 2.2, the current across, which is RL, is the voltage, because in parallel, voltage is the same. So that is V over the impedance across them, the coil. So the voltage, remember, 180 over this impedance, that is 97,841. So this is going to give us the current across the coil. And that was going to be 1,8402, 3 decimal places. Just, if you can just leave it like that. So that is the idea there. All right. 2.3 IC, that is the current across the capacitor. So across the capacitor, we just have a capacitor here. The voltage is the same. So we just have a single capacitor. There's no resistor what? So we need a reactance. There we are going to work with a reactance, which is XC. So that's 2.3. So the current across the capacitor from the voltage over the reactance across the capacitor. So that is the idea there. So we can calculate the reactance across the capacitor. Remember XC, if you've forgotten this from your formula sheet, it is given XC 1 over 2 pi FC. So you can go back and take off your formulas. So that is 1 over 2 pi FC. So that is our XC, which is the reactance of the capacitor, is going to be 1 over 2 pi times the frequency, which is 50, times the capacitance. Remember, that is 150 microfarad times 10 to the exponent of -6. So that is going to be our XC, 21,221 ohms. So this is something that you're going to have as your XC. So remember, the reason of calculating XC is because we need it. The reactance is just like the resistance. So having a voltage of 108, which is the same in a parallel combination, divided to the reactance of the capacitor, 21,221, you're going to obtain the current, which is flowing across this capacitive circuit, and that is going to be 8,482. So that is how you can calculate this. So many formulas, but these formulas, they're just relating to one thing. Just one thing. All right, so that is, we've got our current. Then 2.4, the horizontal component of IRL, which is from the component of the current that we calculated across the coil. These are the components that you are referring across the coil. So that is the component. How do you determine these components? All right. Remember, guys, where we calculated IRL, this one, it is the current that we calculated in this coil where we have got a resistor and an inductor. And remember, when I referred you back to the normal RL circuit, okay? When I referred you to the normal RL circuit in series, remember this is the RL in series. We saw what we ended up having. So in terms of the voltage, or in terms when you are presenting in terms of the current, you are going to have the phasor in this manner. So this is for the current. So I want us, remember the total current, gonna have something of this nature. So this current is the current that is flowing across the coil. So this is the current across the coil, which is our RL. And the angle that we had that across in between, which is our phase angle in that inductive circuit, it was 39,955 degrees. So according to the components, guys, we know these components from our science. We've got the horizontal component, vertical component. So the horizontal component definitely is going to be represented as IRL, the cosine of theta L, which is the angle that you calculated there. Vertical component, IRL, the sine of the angle that you calculate, which is the phase angle of the inductive circuit that you're given. So these are the formulas that you are given if you are to consider here. They are giving us IC as IRL sine theta L. This is representing the vertical component of IRL from the vertical component. So if you have this idea, you can take it now to even have the horizontal component and so forth. All right. So that is how you determine the components when you're dealing with the RL. You take where you were having the angle between the resistor and the inductor, which is the phase angle between the resistor and the inductor. It was 39,955. So remember, IRL, we calculated this current, it was 1,84. This current we calculated, it was 1,84 amps. So we can calculate these components. All right, so the first part, it is to calculate the horizontal component of this. All right, so let's calculate the horizontal component. All right, this is our diagram here. So that's going to be 2.4. So the horizontal component, you can even write it as this one, horizontal component, referring to the current in the coil, is given as, that is IRL, the cosine of theta L, which is the angle that is between the inductive circuit. So IRL, we calculated this 1,84, the cosine of the angle, which is 39,955 degrees. All right, so that's it. And this was going to give us 1,411 amps. Okay. So that is for the horizontal. Then for the vertical component on 2.5, if you check 2.5, is for the vertical component of the same current IRL, this one. So, but now we need the vertical component. And like I said, in this case, this is our vertical component. So 2.5, the vertical component, you can just write this as vertical component. All right, so this is given as IRL, the sine of theta, which is the theta that you calculated. So that's 1,84, the sine of 39,955 degrees. Okay. So that was going to give us 1,182 amps. So that is how you calculate this when dealing with the coil. All right, then the other part, they still need you to work with the components to determine the horizontal component of IC, which is the capacitive, working with the current that is in this. So this is considering this circuit alone in this branch here alone, this branch, there's only a capacitor, just a single capacitor there. So meaning to say you refer that part as a purely capacitive. And remember the properties of a purely capacitive, that the current leads voltage by 90 degrees. So they will be separated at 90 degrees. So therefore, the horizontal component is going to be IC, which is cos theta, but the angle is 90 degrees. They are separated at 90 degrees. Because you are referring to theta, which is the theta that you're talking about is the theta, the angle of the capacitance that you're given, and it's 90 degrees. So it's the one that you use is the same angle that you even use on the vertical combo IC sine of 90 degrees also. This is how you calculate. So this is your horizontal component, and this is your vertical component. So we can calculate these from IC because they're taught from IC. So where is IC? It's on a purely capacitive circuit. There is no resistor. What is just a capacitor only? So that means we can calculate the horizontal component in this case. So the horizontal component of the current across the capacitor is going to be given as that current across the capacitor, cos theta, which is the one for the capacitive circuit, and that's IC. We got this as 8,482, the cosine of 90 degrees, and that is going to give us 0 amps. All right. Then we can also calculate the other one, which was 2.7. It was the vertical component of this IC, and that is 2 marks for that, which is the vertical component of IC. So in the same manner, the vertical component, that's IC sine 90 degrees. So meaning to say, we can calculate this. So the vertical component of IC can be calculated as IC the sine of theta, which is the angle that is affecting the capacitor. It's a purely capacitive, so that will be at 90 degrees. So that's 8,482, the sine of 90 degrees. And that was going to give us the same 8,482 amps. So that's it. Just like that, we have got the components. So be careful how the question is given, how the question is presented. So these are the typical questions on your AC. Shall have more questions as we move on, but for now, that's it. Till we meet again.